Okay, it's 9. Shall we start?
Sounds good.
Hey, Routing Working Group. Welcome everyone to IETF109 virtual, unfortunately. Please. So Jeff and Chris here and Ingen, our great secretary. Next slide, please. So please read not well. It's a reminder of IETF policies, and by participating in IETF, you agree to follow IETF process and policies. There's a number of documents you could read to learn better about IETF process and policies. Next slide, please. IETF policy with regards to IPR disclosure is in RFC 8179, Routing Working Group specific process. We have two main gates, one at working group adoption, one at last call. And unless everybody responds to IPR call, document is not progressing. So there's a document that has been waiting for 11 months for responses from everybody, and it's a really bad example of how it should not be done. Please do respond to take IPR calls seriously. Next, please. Agenda review. So a very busy agenda, exciting one. So you see there are many drafts that are related to segment routing protection. Spring chair sent an email today asking for clarification. There are about 5 or 6 different drafts being presented, partially in routing, partially in Spring. So we are going to meet and discuss where they belong and where it makes sense to follow, because some of them are very related to TI-LFA, so they obviously should be in routing. Some of them are closer to encoding with regards to Spring. So the question is open. We'll discuss it and potentially organize interim with both Spring and routing chairs and all of you to decide what we do. Because again, SC, thank you for bringing it up, by the way. Next slide, please. So we've got one document that passed working group last call, policy model, waiting for write-up. So Chris, I believe it's waiting on you.
Yes.
Next, please. So no RFC is published since last IETF. Next slide. So we've got 2 drafts that are expected. So BGP peak is the draft I mentioned before, is still waiting for IPR responses. So I clearly remember CISC patenting it 10 years ago or so. I also mailed Clarence and asked for clarification. So hopefully we should be able to solve this soon and actually go through working group last call. Another document is Jan Crib extended. From my point of view, very ready for last call, so expect let's go working group last call soon. Next slide, please. So that documents that are working group documents, I believe we still have not achieved consensus on progress, so it's still being discussed. And we'll update you when we have reached consensus to do it one or another way. Next slide, please. The SR-V6 egress protection has been recently adopted, actually IETF107, I believe. So this is one of the documents that's going to be discussed as well with regards to all of protection schemas for segment routing. Next one, please. So there are a number of ongoing documents. The TI-LFA has been updated day before yesterday, so thanks for updating. It looks really good. ATN BGP has a bunch of very interesting discussions ongoing. RPM model and QoS models are getting very close to being ready for working with last call from my perspective as well. Next slide, please.
Yeah, I think that's it.
Oh, here, that's the last slide.
Yeah.
Okay, we are moving to Stefan.
Hey, Jeff. Hey, Chris. quick question regarding the TILFA draft. I think we are good regarding the updates, and we have reduced the number of offers to be compliant with the IETF rules. Could we put this document into the working group last call queue?
We will do so. So we will handle your request as formal request, and we will look at updated document. I didn't yet. I saw the email. And
yeah, just let me know if there are additional updates to do. Okay.
Sure. And thank you.
Thank you.
Dean Bogdanovich.
Hello, can you hear me?
Yes, we can hear you.
Okay, great. Thank you. Next slide, please.
Yeah, I'm going to full screen mode to get the full effect here. Go.
And then next slide.
Yep.
So just a clarification for presentation at this group. We are asking here for actually we're looking here to raise some awareness for the problem that we are seeing, and there is a question of how to do the most effective garbage collection routine in the configurations. But some of the proposals that we could do have some dependencies across multiple systems. This work is currently being started in the IRTF, but the natural home is the ops area. But there are certain dynamics that are touching routing, and having some understanding of how changes in the routing can be done, that if what will come to that, if we change one part of a routing at one of the config levels, that it will not have a global impact on all the across all the levels of the configuration. And that is something that we hope people within the routing group will be able to help us. So please view this as an introductory and informational only for people, and maybe some of you will be interested to join our work. And for us, the main motivation is that that as the configurations are growing, and the network operators, especially in the BGP policy and QoS areas, are starting to be afraid should they touch something or not, as it's been in there forever, and they don't know if they change some of those entries, what will be the outcome. And that is a major problem because it grows, but as somebody said, it also kills human brain cells, wasting their time over something, trying to figure out if it should be there or not. And for a variety of reasons, the configs are growing and they are not getting optimized. So having all this information multiplexed in a single file is growing to files of about 50 megabytes and larger. And there is a good question, should those files be that big? Some of the network operators have centralized all the config in a database, and they are always trying to sync the actual device configuration with the database, but still those things get out of sync during manual interventions. In one of my previous experiences, we were trying to add programmatic control for certain network services, but the question was how to act when there is a manual change done by the operator, and how to treat that, because it doesn't matter how good your protocol and network operation process is. When a operator gets on a physical device and logs into that device, changes are being done, and the question is, should they stay there, or was the whole process correctly followed? Next slide, please. So where do we see that the multi-level configs could help? One of them is service assurance and network slicing. We will talk a little bit more about those two examples a little bit in the next slides, but also in network migrations and merging of the configurations and server levels, as well in zero touch provisioning. So with the if we have a large service instances that we are looking to add to the network, if we are trying to do that in one large file, it's a question where all those things have to be added correctly. By being able to split it up in multiple levels, we believe that this can be simplified and it can be done in several smaller steps, making sure that the correct configuration is being done. But in case also something is wrong, it should be easy to remove one of those levels. And pretty much the same thing is with the zero-touch provisioning, where incremental additions can be done after verification that the network device and the network service have been correctly added according to the original intent. Next slide, please. So the service assurance is a very interesting example. The draft, Benoit's draft for the service assurance architecture is essentially a closed control loop system that modifies the running configuration and verifies that the intent and the configurational and the network operational state are in sync. And the idea there is that you can verify also the SLAs, and this requires a lot of active and active changing of the network configuration. Now, if this would be done in the older ways, trying to manage all those config changes is a complex task. Some of the operators have solved that problem to a certain extent, but it has been done with large teams, and it requires a lot of energy to be added. We believe, the draft authors believe, that by creating multi-level configuration and being able to design the correlation between the services and the basic functions of the network, the service assurance architecture would be easier to implement in today's networks. Next slide, please. The other area is with the network slicing. Again, as besides in network slicing, we have to we can view it from two perspectives. We can view slices as address slices, but we also can view it as separate management slices, where the management slice could be, sorry, where the network slice with management isolation could be created by using logical elements on a network device. And the issue there as well is how make sure that in case there is no full management separation on the device, how can be created a separation of the each slice configuration, that those will not be conflicting with each other. The slicing brings two dimensions. One of them is the now this. Oh, actually, let me finish and then go to the next slide. So the as the slicing configuration can be hierarchical and recursive, we are here creating a multi-level, a multi-dimensional problem. Can you please go to the next slide? So we can have, let's say, the provider network is across multiple slices, but they are hierarchical in a vertical sense. And now when we want to add multiple customer slides, we are adding another horizontal layer where the customer slice of the customer, let's say the red slice, is in parallel with the customer blue, but hierarchically they are going both on top of the provider network. And the question is also now how we can most efficiently manage those configurations without multiplexing them all in one in one file. How we can enable the red slice customer to create their own changes that will not be impacting in any way the blue customer slice, and making sure that those are also isolated from the management perspective, not just from the addressing. Next slide, please. So one of the proposals, well, actually one of the ideas that we have is something that was discussed 7-8 years ago within the RESCONF proposals, and creating multiple panes of glass that are being where each configuration increment is viewed as a pane of glass that is being overlaid on the top of the previous ones. And with that, we can create multiple levels as well, making sure that the syntax and the semantics as you are growing are being correctly correctly done. So with this, it's also important to say that each level can be handled in an independent manner, and there's still one area of research. Should it be an atomic function, or can we change some metrics on an atomic function that will then have impact across the whole routing protocol, or it can be that isolated in a certain it can be isolated just for a certain instance. Next slide, please. So as said, we are presenting this to here in the routing working group, but also in the NMRG. This is just a start, and we are looking to collect feedback and problems that the community might see with our proposal summit, if you have some additions, as well with the idea that we have for a potential solution.
Tony?
Moving to netconf and openconfig, how do you see levels playing out within the hierarchical structure that they've already created?
So that is one of the problems that we are looking into it. As said, we are starting to look into it because it's a growing problem, but don't have a good answer for that now. It's a good one to write down, and I know Zhu Feng did a little bit of looking into that, but this is the area that requires much more work. As I said, it's the beginning of it.
Okay, no more questions. Thanks, Dean. And indeed, it's a large topic, and it's going to affect potentially what we have done last 5-6 years with data modeling. So I'm really looking forward to future work here.
Okay, thank you.
Thanks. Shushan?
Okay. Thank you, Jeff. I will introduce our work about SRv6 midpoint protection, presenting other orders. Next slide, please. Oh. Okay, thank you. This page shows the overview of midpoint protection mechanisms. Actually, our proposal is quite straightforward. If an endpoint indicated by the segment list in a loose SRv6T path, there are 3 steps during the convergence, as the slide shows. In the first step, the IGP is not converged yet. The adjacency of the field endpoint will perform as a repair node. In this picture is node B, and send the packet to the next endpoint in the segment. In the second step, IGP has already converged in some upstream nodes of the failed endpoint, maybe B or maybe A in the picture. There is no routine to E in the fib of these nodes. So these upstream nodes will be the repair node and perform the proxy forwarding action again, send the packet to the next endpoint in the segment. In the third step, SRv6 policy has already converged, and the node E has already been removed in the segment list, so the nodes will forward the packet along the converged path directly. Next slide, please. This is a brief history of this document. In version 0 and version 1, we mainly focus on the mechanisms definition. And in version 2, actually based on the discussion about security in the IETF community, we also add a section to provide security consideration, section 6. Basically, we limit the proxy forwarding behavior in SRv6 domain. And in version 3, which is the latest version, based on the discussion in Spring mailing list, we discussed the case that some endpoint that cannot be passed. Here in the slide, we just read an example of this. Maybe the endpoint is a firewall and it should not be passed at all. So in this case, we will refer to some other work. We give an example of the document which will provide some mechanisms to solve this problem. And next slide, please. We believe the document is virtual and the solution is straightforward. So we think this is ready for working group adoption. Of course, more contributions or comments from the community is also very welcome. Thank you.
I think you're on mute, Parag. Yep.
Can you hear me now?
Yes, please talk louder.
Yeah, so I want to just ask, like, how do you differentiate a condition when the route being not present versus the link down, right?
Sorry, can you repeat your question? I
So in the
haven't.
SRv6 packet, when we look for the destination lookup, how do you differentiate? Let's say that the locator route not present being the link, you know, the what you described, right? You will jump to the next segment list and forward based on that.
Yes, that is the proxy forwarding defined in this document. You mean how the packet or the node decide whether to execute this behavior?
Yes. So there are two conditions, right? Whether the IP prefix or IPv6 prefix not been advertised itself, or it is just withdrawn because of the link flap or other event.
Yes. Actually, this is described in the three stages. Maybe we can go back to the slides too, I think. There are three stages. When the IGP is converged and when the IGP has already converged, we cannot find the routine to E anymore. So we just some upstream nodes will do the proxy forwarding, and if there is no IGP convergence yet, the node B, the adjacency of the failed node, will know that something wrong has happened, so he will do the proxy forwarding. That is two cases.
So what will happen to the function which is supposed to be executed at the node E?
You mean the function should be limited to some nodes?
No, the packet, I mean, in the ideal condition, packet should go to E, right, from B. And the SRv6 some function need to be executed, right?
Yes, because there is something wrong in E, right, in node E. So the node B just do the proxy forwarding. As the
Maybe
picture
some
shows,
accounting, yeah. So maybe some accounting related function supposed to be executed, or maybe some rewrite which is based on that seed, right? So I think
actually there is no extra. If I understand your question right, you mean whether something new functions should be ended in some segment in the seed for E. Is that your question?
Yeah. There
that
can
is
be a
not the
multiple
case.
conditions, right?
Yes. Actually, the E node, it can be, for example, just an endpoint, maybe end.x, or maybe it's just can just some other functions. But if the node B do the proxy forwarding, it just can do the function about forwarding the packet directly to the destination. If there is other functions should be maybe some other functions should be executed in node E, it cannot be proxied by node B, just forwarding the packet directly.
I mean, can we use TILFA here at node B, right? Then we can avoid this situation. The node B link down and we will converge because we already programmed the backup path.
Actually, there are
that
some
would be
cases.
A better, right?
There are some cases have been discussed in the document. Different types of B. Maybe it is just a transit node, or maybe it is another endpoint in the segment list. So we in the different classes of node B, we have some different cases and discussed in different sections in document. But for different types of node E, for node B, if it will do the proxy forwarding, it just can do something like end. Maybe just find the next segment and forward packet to node D in this case. There are some different scenarios.
Yeah, so the ideal would be to use the backup path to reach E via some other mean, right? Via TILFA.
Yes, a backup path to next segment in the segment list in node D. Actually, it skip the failed node E and just go to the node D directly. That is the basic idea here.
Okay.
I think you're not converging on questions and answers.
Yeah.
The
Yeah,
parent
you
question,
can go. Yeah.
yeah, what he described, you could use TI-LFA to get to node D, which is PQ node in this case, right? I would like you to take it to the list because we are going rounds here and continue with Stuart.
So I'm afraid my question was very similar. When you set up a segment routing path, you set that path up for a reason. And that reason may be that you want traffic to go to a particular node for a particular reason, or you want to protect other paths from being overloaded by that traffic. So with all of the repairs and alternates, I get really worried that you're going to bust all the original reasons for creating the SR path. And I would imagine the only node that could actually reroute a path is the head end node, which has the whole network at which it can to choose from, as opposed to a node in the middle, which could be busting someone else's SLA.
Actually, I think that is a very good question. I can respond the question in two aspects. The first one is that if some node cannot be bypassed, we have some mechanisms that are already been referred in the document. Maybe some node, maybe in this node E, it cannot be bypassed. It performs the firewall to the whole path. So it can, for example, extend the IGP and to advertise that I cannot be bypassed, so do not bypass me. This is the first solution for that. And the second one is the motivation for this solution is just to give a method to supplement the TI-LFA mechanisms. If maybe something wrong happens in the endpoint, and we can have some method to bypass the failed node and to go to the next endpoint, at least the packet will not be lost, right? And the flow will not be interrupted. So that is the motivation here. Okay, that is my response. So I think the mechanism itself is reasonable and it can solve some problems here.
Well, you can be sure you're not going to bust something else, then fine. But it's quite a complicated problem, I would imagine, making sure you aren't going to bust some carefully engineered traffic plan.
Dave Sinecroft. You're on mute. Dave, we cannot hear you. Okay, Robin.
Hello, can you hear me?
Please be quick. We've got 1 minute left.
I just use a quick that regarding the flag, the comments. I mean, the first one, the other function on the E to be executed. From my point of view, that's the different function because this is just for the protection on the end and the X function. I mean, so that's a different scenario. The second one, I mean, the confused. The confusion always happens between the this mid protection and the TRFA. From my point of view, I mean, so that's because this is the SR traffic engineering scenario because that's the segment list will go through the E node. So that's when the E node is filled. So you need some this the special process in the B node. That's the proxy file forwarding because they need to reduce some this the SL and also the move the pointer like this way. So that's the different scenario. If possible, this can be explained in the mailing list for details. Okay.
Yeah, so reading the draft, motivation is unclear. I mean, I can kind of understand what you're trying to achieve, but it's not clear really without proper understanding. So draft is definitely not ready for working group adoption. And please maybe ask someone else to read it and tell you what's unclear, because yeah, it's very difficult to understand what you're trying to achieve. And I have a question about experimental track on it. I mean, you don't define any new extensions, you're kind of defying possible behavior. So probably informational would be better track rather than experimental.
Actually, there are some new behavior defined for repair node. For example, to do the proxy forwarding for node B, we define some SRv6 functions. So there will be some new functions defined in this document. Okay, maybe
okay, then I'm looking forward to reading new updated version of the draft, and I think we are going. Bruno, please be quick if you have a comment.
Yes, sorry. So it's not about fast reroute, it's about terminating a segment and trying to process the next segment or whatever you find behind the first segment. So I think it would deserve some discussion in the Spring Working Group. As we can see, it's about SRTE, SR policies. And also, as we've discussed with Jeff, there are multiple documents related to terminated an SRTE path or a tunnel, and we need coordination because they are related subjects. The main subject is so it's not about fast reroute. You're terminating a tunnel. So what do you do? Whether it's a VPN, whether it's a SRTE path, whether it's a service function. It's a bigger subject. I think it deserves a larger discussion.
Thanks, Bruno. And yeah, I agree with you. So we are moving on. And please post your questions to the list. It should help authors to publish new versions. That's going to be better and more clear. Thank you.
Thank you.
Shraddha?
Thank you.
Hello, can you hear me?
Yeah.
Okay, I'll talk about Anycast egress protection for segment routing networks. Next slide, please. So we have on the agenda introduction what we are trying to do and what is the proposed solution for different kind of underlay tunnels like SR-MPLS, SR-M6 and SR-V6. Next slide, please. So what is the use case? So when you have a network with multi-home services on the PE node, when the PE node fails, you can protect the traffic by sending it to the multi-homed PE node so that the traffic reaches the CE and traffic is not dropped. So another alternate for this could be do this from ingress, which is the BGP package. But this is an alternate solution to that where you protect the traffic on the egress itself. So, and you can provide faster protection with egress protection mechanisms. Like you can do a 50 millisecond convergence in this case. So there is an RFC 8679 for egress protection framework, and the solution that we are proposing is based on this protection framework. And we see some possibilities of simplifying this in SR networks, and that's what we are proposing. Next slide, please. So let's see how this solution works for SR-MPLS networks. So CE1 is multi-home to two PE nodes, which is E and P. And there is an ingress node. And R1 PLR and R2 are the P nodes. So an Anycast loopback address is assigned to E and P. And this Anycast IP address corresponds to the context ID as specified in the egress protection framework draft. And there is a SID associated with this Anycast IP address. For example, SID 10 is associated with this Anycast address here. So once the Anycast addresses are defined and Anycast SIDs are defined, the protection for that IP address as well as that SID will be can be programmed by the protection mechanisms available in IGP, for example, TILFA. So if this PLR to E, if this link goes down, there will be a TILFA path which will point to the other P. Similarly, when the node goes down, egress node goes down, TILFA will also program a backup path on the PLR which points towards the node P. So so when the service prefix is advertised from E and P, they will use the context IP address or the Anycast IP address in the protocol next hop. For example, if you see on the right hand side, there is this 192.1.1.1 prefix. This has a protocol next hop of 1.1.1.1. Similarly, P is also advertising the same 192.1.1.1, and it is sending the same protocol next hop, which is this context IP address. And if you see the label associated with the service, the VPN prefix, it's the same label, like it's statically configured on E and P, the same label for that service prefix. For example, LB1 here, and on P also LB1. This is kind of provisioned. When the VPNs are provisioned on E and P, the static label is also provisioned on those devices. And this static label comes from the SR-LB label space, which is the SR local label space. And that label space should be synchronized between E and P. For example, let's say we are saying 1000 to 5000 is the SR local block on E. There should be an overlapping or the same covering the same label space available on P as well, so that the same label can be picked up and assigned to the VPNs. And on the ingress, if you see, the tunnel is created for this 1.1.1, which is the Anycast IP address. And then the label stack, let's say we have 1020, 1030, and the last label will be the Anycast label, which is 1010 in this case. We have taken a sRGB of 1000. So the SID is 10, and we have this 1010 label as the last label in the tunnel. So now, if the node E goes down, then the PLR will forward the traffic to towards P, and then we don't need a context label or mirror label or any of those mechanisms, because we are provisioning the same label on both the E and P. And when the traffic arrives on P, it understands the meaning of this label LB1, and it will look up the VPN table and forward accordingly. Next slide, please. So this is a case when there is another CE, for example, CE2, which is multi-homing onto P and another P node, which is a P1. So in this case, we will need another Anycast IP address, so that the backup path is the traffic is correctly forwarded to P1. CE2's traffic is correctly forwarded to P1. For example, we have this another Anycast IP address 2.2.2, and this Anycast IP address is configured on P and P1. And the protocol next hop is set for CE2's the prefixes that advertised by CE2 will have a protocol next hop set to 2.2.2.2. And the other procedures, like the traffic which is ingress is sending towards CE2 will use a tunnel which has the bottommost label as 1020, which is the Anycast SID for us allocated for this 2.2.2.2. So for every pair of multi-homed pair of PEs, there should be one Anycast IP address. Next slide, please. So that was the procedure for SR-MPLS. So we'll see how this can be done for SRv6 networks. So instead of Anycast IP address, we will need an Anycast locator for this solution in SRv6. And the same n.dt4 SID to be allocated on E and P. So so imagine there is a tunnel from ingress. There's a source address which corresponds to the ingress node, and then there's a destination address which directly corresponds to this n.dt4 SID 1::16/128. So so because this 1::: is a locator advertised by both E and P, so there would be TILFA backup paths properly programmed on the PLR, which and with TILFA node protection enabled, if this if there's a failure on E, the TILFA backup path will take the traffic to P. And then because 1::16 is the same DT4 SID that is allocated on P, it will do the lookup and forward the traffic appropriately. Next slide, please. So same solution. So the principles of allocating static the Anycast address for the PE nodes and the static labels for the VPNs, that remains same for SR-M6 as well. So the solution is very similar to SR-MPLS. The difference is the forwarding uses IPv6 data plane instead of MPLS data plane. So if you see on the TPF tunnel payload forwarding information, that LV1 is allocated same on E and P for the for that VPN. And similarly on the ingress, there the TPF information will be sent from the ingress in the destination options. And this the destination address that ingress will use for sending the traffic is 1::1, which is an Anycast loopback address on E and P. The difference here is it's just a loopback address. There is no need to allocate a /64 or /120 or whatever. Just a common loopback between a pair of multi-homed nodes is good enough for SR-M6. Next slide, please. Yeah, so we request the working group to review and provide inputs on this document. Any questions?
Thanks, Shraddha. Bruno?
Yeah.
Bruno, you are in the queue. Are you going to talk?
No, sorry. I thought you would remove me from the queue. So.
Okay, done. Greg? Greg, cannot hear you. Stefan, go ahead. Cannot hear you either. I think you need to unmute yourself.
Is it working?
Okay.
Yeah, it is working now.
Ah, okay, cool. Hey, Shraddha, quick question. Could you elaborate more on how you are allocating the service labels from the SRLB? Is it, are you expecting to do only per verf label allocation in this particular case?
Yes, Stefan, that's right. It's a per
Okay.
verf.
Okay, so you cannot make it working with a per prefix label allocation.
Yeah, that will be just too much operational overhead, I think.
Okay, but this is something that you may have to clarify in the draft because
Yeah, sure.
this part is not well detailed.
Yeah, sure, I will do.
Thanks. Peter? Peter, unmute yourself.
Trying.
Yeah, I can hear you now.
All right.
You tried well.
Okay. Hi, Shraddha. So I have two comments here. So first was similar to what Stefan was asking. It's basically this. I can see this working in a pair wave allocation. If we go to a pair next hop, it becomes way more complex to synchronize the seeds or the labels between P's, especially if we have multiple P's, like not just two, but even more. And the second question is, well, this looks like more like a deployment guide. It's not really standardizing any protocol extension or anything. I don't know. I always ask people whether these things should really be published as a draft. So that's my comment.
Yeah, because there are other solutions floating around. I think that that this is deploying this way is one of the possibility is as a kind of good informational document. And we got some feedback from the on the draft that allocating the labels statically is a little complicated. So we're also working to get to see how we can automate that, and that would most likely require protocol extensions.
Absolutely, yeah, that's definitely something to look at, because as I said, it can become. It sounds easy if you have two PEs and you use the same label or a seed, but if you do an allocation other than per birth, it can really get more complicated. So, sure. Thanks.
Greg, unless you're really quick, we'll move on. You've got a few seconds, so be quick.
Go to the previous slide, please. Yes, thank you. So the PLR uses TI-LFA based on availability of R2. So I would imagine that you're using some network failure detection mechanism. Have you considered the scenario of double failure when almost simultaneously with the failure of PLR E link, the link R2 to P fails? And when PLR starts sending TI-LFA tunneled payload, what happens on R2?
Yeah, so the multiple failures, there's always possibility that traffic can get dropped or can undergo micro loops when there are multiple failures. That's applicable to TI-LFA in general as well, and nothing special about egress protection. Nothing very different for egress protection.
Yeah,
so
I
we'll
think
take it to the lead. Greg, I think none of IPFRR technologies provides protection against double or triple failures. It's a formal statement. We never claimed anything else. But please do send your question to the list.
Thank
and sure, thank you. Yuja.
Is similar as previous, some concern about the deployment complexity because it requires static assignment of label. And the second one is SR-M6 is still under discussion, so maybe not proper to have reference here.
I would really like us to finish discussion on this draft, but the point's well taken. Thanks, Trishan. Next presenter. Yuja?
Hello, thank you. This is Idro speaking. I'm going to present this diecast in CFN. DynCast stands for Dynamic Anycast. So this is the first time we present this work in RTGWG. We kind of think this is highly relevant to the routing protocols. So I'd like to give a brief introduction on what this work about. And we have an activity, which is a side meeting at Wednesday. So I'm going to also bring this to your attention. Next page, please. So here is a little bit about the background. So this is a typical edge computing scenario. So with the increasing deployment from the service provider for the edge computing for the scenarios like the augmented reality or virtual reality or even the connected cars, we find out there are more and more, there could be a huge number of edges. So it's well known that the reason why we want to adopt the edge computing is compared to the cloud-based computing, the edge is normally more closer to the clients, so it's shorter and faster. So compare with the pure host-side computing, we can somehow make the battery savings, and also sometimes there are data set size concern at the end host. So these are why the edge computing draw more and more attention. So for this edge computing, we figure out there are two features emerging. The first one is there are a large number of edge sites in a city. For example, there could be a couple of edges for each district of a single city. The other one is for each of the edge, it could be a very small one. So that means it only has very limited and varying computing resources. Next slide, please. So what's the problem? Here we try to depict a typical problem. So we are trying to focusing on the computing services. So there are a bunch of computing services with different level of computational complexity. Give a very specific example for the social networking, when you some of the computing services has to be performed at the edge, so that you somehow can make the.
I think audio just died, or just me. Chris, can you hear?
Yeah, I lost the audio as well from Yizhao. She came back for 2 seconds.
So let's give it another minute. If she doesn't come back, we'll try to move to the next presenter and restart later.
Yeah, sounds like a good plan.
Daniel, please get ready. I think we're going to move in a few seconds. Doesn't seem to work. Okay, Daniel Huang.
So Yizhao might still be able to hear us, though. So at least perhaps we can tell her that we can't hear her. Yizhao, we're gonna move ahead with a separate, okay. There we go. So is Daniel here?
He's saying on the chat that audio is not working either.
Let's see.
It is working now, though.
Hello? Hey.
Yeah, I think we can hear you now.
Oh, okay. So
we'll go back to your presentation, and hopefully your audio will continue to work.
sorry about this.
No problem. Can't control. Let's see. Okay, so which slide? So your audio dropped out on this slide here,
Wait.
I believe.
Okay. So okay, so I didn't know exactly where the audio stops, but anyway, so the problem is how shall we optimally route the service demands based on both the computing resource metrics and also taking the network conditions and status into account. So which one is the best one? That is the basic problem we're trying to answer. So next slide, please. So there are some current practices, but actually quite a few of them. So the left-hand side of the picture trying to depict the current practice in an abstract way. Normally, the client would ask for some resolver, probably the GSLB, and ask for what's the URL. Then the resolver would check, for example, for different cities like Beijing and Shanghai, then return an IP address. The client will use that IP address to connect to a particular data center or SLB. Then optionally, it could talk to different edges, and optionally, it can ask the client to redirect to try to redirect to some of the one of the ABCD's edges. So there are some issues we find out. I list some of there for the. Because of time constraints, I don't think I will go through them all one by one. But in summary, to consider efficiency and the latency, we found out they probably have better practice at the network layer. So next slide, please. So here is this slide tries to introduce the concept of the CFN downcast. Basically, the client wants to use a green service here. If you look at, there are two sites, site 1 and site 2. If you look at the very small green circles there, basically they are indicating two service instances instantiated at site 1 and site 2. So the client can send a service request to any of them. So the client will use an anycast address to access this green service. Then it goes to this CFN node 1. Then the CFN node 1 will determine how to route this packet. It will jointly consider the computing and the network load and route this packet to MEC site 2 in this picture. So this would transparent to the client. So what client knows is only the anycast address to represent the service itself, but it doesn't know what exactly the service instance this packet goes to. So the green lines here shows where the data plane, the data flow goes, and there are some control plane requirements as well. So for the brown arrows, there should be some computing service information notification from the server side to the CFN nodes, and also the purple one indicates that among the CFN nodes, there should be some information sharing, both for the computing resource information and possibly for the networking status information. Next slide. This is to get a closer look at the CFN dying cast. First, we want to clarify what's the service and service instance here. So here the service we are trying to target on is are the only computing related services. So if you look at this small box at the left hand side, we have 3 services: blue, red, and green. So each of the service offer one specific function, no matter where it is deployed. So indeed, if you look at right hand side, there could be multiple service instances instantiated at different places. So for site 1, there are blue and green, and for site 3, we have blue, red, and green. So these are called service instances. Next page, please. We figure out that potentially 3 features to be supported in Dynecast framework. So the first one is the Anycast-based service addressing methodology. Then the second one is the flow affinity. Third one is the computing-aware routing. So for the next 3 pages, I will quickly go through each of them. Next slide, please. So the Anycast-based service addressing methodology, if you look at the blue circles here, actually they are the same service. However, they are the 2 different instances instantiated on at different places, which means the service instances 2 attached to CFN node 2 and the service instance 3 attached to CFN node 3. So we would require some of the Anycast-based service addressing and kind of map to an unicast IP address-based binding ID in order to reach the specific service instances. Next page, please. So this page tries to talk about what the flow affinity is. It simply means select the best edge and stick to it. So look at the picture here. We have 2 clients, and flow 1 and flow 2, they possibly trying to use the same service. So once the service instances to handle each of them has been determined, it has to stick to it. So flow 1 always goes to the upper blue circle, and the flow 2 always go to the lower one. So possibly we would require some of the binding tables in order to ensure the flow affinity, and also we would require some of the procedures at the data plane to make sure the flow to ensure the flow affinity. Next slide, please. This slide talks about the computing aware routing. Basically, there are 2 parts of it. And the green circle talks about there would be some service information notification from the service side to the CFN node. Here, the service information normally refers to the computing resource related information, or sometimes we call it the computing metrics. This is the first part. The second part is the blue arrows here. These are all the information sharing or distribution among the CFN nodes. So that could be the computing metrics and the networking metrics. Next slide, please. So to recap, we have 3 features to be supported: Anycast-based service addressing methodology, flow affinity, and computing aware routing. We figure out there could be some work required, like how to represent the computing metrics in the defined service and the service instance context, and also how to distribute this metrics, what are the formats should be, and how frequent the updates should be, and also how to use these metrics in the route determination. And for the data plane, the definition of the requirements for possible data plane extensions and procedures, these are also one of the possible work. Next slide, please. We will have a virtual side meeting on this with the purpose to first to understand the problem space and try to review the framework, and also to discuss the potential work. and where to fit them in IETF. The time will be the Wednesday, 5 minutes after the plenary ends. So we also have the WebEx information here. So your help or your comments or suggestions are welcome.
Thanks for the presentation. So we're not going to take any questions here. If you're interested in routing working group opinions and questions, I would really advise you to send emails and explain what you're trying to do and ask for comments. And thank you for the presentation. Okay, Daniel.
Can you hear me?
Yeah.
Okay. Good morning, good afternoon, everyone. Thanks, Jeff and Chris. This is Daniel Huang from CT speaking. And firstly, I'd like to make a clarification about the slides. Actually, the slides has been presented in IETF109 by my colleague Chuan Xiong. But during the past 3 months, we made a couple of minor changes. And actually, this slide is about a summarized presentation about the 2 drafts, which is a problem statement of the precise transport network and the requirements, respectively. Next slide, please. Okay. In addition to the enhanced mobile broadband service and the massive machine-type communication services, an important outstanding communication service feature offered by 5G network is the ultra-reliable, no-latency communications, which addressed the vertical industries, such as the Internet of Electricity, Internet of Vehicles, and remote medical and augmented reality or virtual reality, just to name a few. When it comes to deterministic networking services and time-sensitive networking services, as is discussed and designed in TSN and .NET, the technical network service requirements from this kind of vertical industries usually goes far beyond the deterministic and time-bounded latency. For example, when it comes to the Internet of Electricity, sometimes we need hard isolation or service isolation for a specific service and transport service. And when it comes to the Internet of Vehicles, it always to get involved with the operator networkers and administrative network domains. So there's going to be cooperation, coordination among multiple network operators and administrative domains. This is a general summarization of the use cases of precise transport network. And next slide, please. Okay. This slide is actually, I'd like to make a detailed statement about why we call the precise transport network right now other than deterministic networking as in .NET or time-sensitive networking and TSN. Simply because there's the networking service requirements goes beyond the latency, bounded latency, and jitter and packet loss in TSN and .NET. There's more precise latency and precise packet loss, as well as jitter. Actually, it's about fine-grained technical requirements in terms of the latency, packet loss, and jitter. And when it comes to resource reservation, as it is designed in TSN and .NET, is I'd like to coordinate the coarse grain resource reservation. But when it comes to the precise transport network, we need to design a much more fine-grained resource allocation mechanisms, such as service isolation and more flat size resource isolation. And also in TSN, we designed a cycle and queue processing mechanism to guarantee the bounded latency and the bounded packet loss and jitter. But in the use cases, as I mentioned in the previous slide, this kind of mechanisms are not enough to address the requirements. So we need some kind of other mechanisms, such as the flexible slicing and talos. And in deterministic networking, actually, we designed the mechanisms in a quite closed group of administrative controlled domain. But when we're talking about the use case of an Internet of Vehicles and augmented reality or virtual reality, there's the service will get involved multiple network administrative domains. So we need just cooperation and coordination mechanisms among multiple administrative domains and the multiple operating networks. That's the major difference between the deterministic networking and TSN and precise transport network, which stated in these slides and in the. And next slide, please. Okay. When it comes to the problem of the existing mechanism and technologies to time working, when we're talking about traffic scheduling mechanisms such as shaping, queuing, and scheduling mechanism, which is designed to guarantee the bounded latency and packet loss, reduced eliminate packet loss and the jitter. We depend on the dedicated time synchronization mechanisms. But when we deploy this kind of mechanisms in near 3 networks, the network will be overwhelmed with unnecessary burden with the costly time synchronization mechanism. So this is the problem. So we need new candidate to address the same requirements in the near 3 network scenarios. And when it comes to the link delay, when we're talking about local area network scenarios, the link delay actually could be ignored in most cases, in most scenarios. But when it comes to long distance transmission, the delay and the jitter incurred from the long distance transmission could not be ignored, and they have to be addressed carefully with the sophisticated mechanisms. And in both TS and DetNet, we used the flow aggregation mechanism to address the traffic flow treatment. But when it comes to the use cases, as I mentioned in the first slide, there's dynamic flows from multiple users in a lot of vertical industries. So our customers, they simply don't want their flows to be aggregated in coarse-grained treatment mechanisms in TS and DetNet mechanism. They need a special and more precise traffic flow treatment mechanisms services. And also in the both time and security critical service scenarios, they need service isolation for the burst, for the bursty traffic or something like that. And also they need more fine-grained resource allocation for the service. Next slide, please. And this is simply generally a summarization of the requirements to a precise transport network. I don't want to recount it one by one because I already stated in the previous slides. Actually, I don't think this is an exhaustive list, and more requirements could be updated upon more discussion and more input. Next slide, please. So as I mentioned in the previous slides, in the precise transport networking, especially from a point of one-to-one end-to-end precise transport network service, and we get involved the multiple network operators, and we need precise, more fine-grained customers traffic flow treatment, and we need quite precise network resource allocation and the service isolation. So we would suggest and propose some new technical mechanisms or extend the existing mechanisms and technologies such as DATNet and segment routing to address the problems and meet the requirements as it's stated in this draft, as well as the slides I presented in the previous slides. Next slide, please. Next, because this is simply the second time we presented the slides, firstly, your comments, the suggestions, the questions are really very welcome and greatly appreciated. And we will propose, furtherly, we'll propose the framework and solutions for precise transport networking upon your input or comments and suggestions. Thank you.
Thank you, Daniel. I see there's no one in the queue, so Greg is next, I believe.
Ready when you are.
Go ahead. Greg, you can go.
I don't see slides. I see old slides.
I do see your slides. It's weird.
Yeah. So what are you seeing, Greg?
I see the slide from Daniel.
Okay.
Okay, let me. Okay, I'll try to refresh.
I assume you're seeing, Jeff, the multi-point.
Yeah, I see the right slides. Yeah.
Okay.
Okay, so this is on multi-point VFD in VRP use case. We discussed this some meetings ago. Next slide, please. So of the motivation, VRPv3 allows for fast detection of the master down at 3.3 milliseconds, and backup router uses the master advertisements to monitor the master. At the same time, it could be achieved using BFD. RFC 5880 defines point-to-point, but now we have RFC 8562, which defines BFD for multi-point networks. The problem with their point-to-point is that it creates, in a synchronous mode, bidirectional BFD session, and the master doesn't really need to know the status of the backup, nor it needs to know the identity of the backup. Next slide, please. So the advantage of BFD for multi-point networks, which is published as 8562, it allows to use BFD with the silent tails, and it uses demand mode in BFD. It updates the RFC 5880 so that the session can start in up state when the root or multi-point head start transmitting BFD packets. But some can see it as a disadvantage. There is no three-way handshake, so the tail cannot use value in a your discriminator field to multiplex BFD session. So thus, it needs to use a combination of my discriminator value, source IP address, and their link on which it received. So which requires their bootstrapping mechanism for point to multi-point BFD session, so the value of my discriminator used by the root or master, in this case VRP, is known to the backup routers. So next slide. So what we propose is a very small extension to VRP control packet that would include their discriminator information used by the master. Next slide. So how it works, the master router creates a BFD session as type of multi-point head and starts advertising the value it allocated in its VRP control message. A backup router at some point receives the control packet, and if it supports this extension, creates a BFD session as multi-point tail. There are certain dependency, as I mentioned earlier, that the tail needs to use IP address in a BFD packet to demultiplex BFD session, so that their address of master used in a VRP message must be the same as source IP address used in a BFD control packet. Next slide. And once backup router notices missing their or determines that misses a number of consecutive BFD control packets, it can may start re-election process. So there is some thought that we are starting with the offers, and actually I mentioned that we have a new co-author, Gayan, and we welcome him. And we started discussion that possibly using not only silent mode of BFD for multi-point networks, but using some active that are defined in RFC 8563 and MPLS for point-to-point BFD. So they work somewhat differently, but effectively what it does, it allows the head to know the status of their tail and whether the tail receives BFD control messages from the head. So it's just something that we're exploring, and appreciate your suggestions on whether it's interesting for VRRP to let the master know the status of the backup node, and effectively identity as well. Next slide, please. So comments are always welcome. Discussion, and we think that the base functionality is quite simple and straightforward, and we ask for working group adoption. Any questions?
Okay, go ahead and unmute yourself, Kausik.
I was just getting ready for my next presentations. I don't have questions for this one.
Okay.
Okay, so should we go to the next presentation, because I believe that it still will be I standing in a virtual red square.
Yes.
Okay, so this has also some history. We discussed it, and we decided to simplify some solution and merge two drafts into one. So this is a BFD over MC-lag interfaces. And again, so Gayan got interested, and we welcome him as a co-author. So now we have 3 authors. Next slide, please. So what's the problem, or what we consider to be a problem? RFC 7130, which is a micro BFD, addresses the BFD over member links of the link aggregation group. So it allows to monitor each member link with a distinctive BFD point-to-point session based on single hop BFD RFC 5881. But that would not work for the MC-lag, which is, again, quite attractive deployment scenario for lag. And one of the reasons is that because source and destination IP addresses, they must be the same on all member links, even though their redundancy group represented by more than one node. Next slide, please. So what we can do if it's IP network, so we propose to use link local multicast address for IPv4 address family, and If it's IPv6, then it's a link local multicast address used at destination IP address. So it's a pretty straightforward. Everything else remains the same as defined in RFC 7130. Next slide, please. So that's where we changed from what we discussed some meetings ago, and I can probably spend some more time on explaining why we propose only IP encapsulation and why we propose to use specific destination IP address for IP MPLS encapsulation. So historically, we were using any address from IPv4 loopback address range, and it's dating back from IP encapsulation for LSP ping. But apparently it was used for creating entropy. Now with the MPLS label at our disposal, there doesn't seem to be apparent reason to have entropy. And in particular, since we are just one hop, being more deterministic simplifies. So for IPv4 address family, we propose to use 127.0.0.1/32 address. For IPv6 address family, all their IP encapsulation in MPLS, we used IPv4 mapped IPv6 addresses. But with some discussions with IPv6 experts, we learned that these addresses, they don't have any special meaning in IPv6. They are not seen as a loopback addresses. Effectively, you can ping them from the host. And the only loopback address defined for IPv6 in RFC 4291 is 1/128. And that's what we're proposing to use for IPv6 family as destination IP address in IP MPLS network encapsulation. Next slide. Again, we are welcome comments, and we are asking for working group to consider adoption of this work.
I see no questions now on the queue. Greg, thanks for your presentation. Kausi, you're next.
Okay, thank you.
Can you hear me okay?
Yes.
Okay. Hello, everyone. I'm presenting extension of Transport Network Aware Mobility Draft on behalf of the other authors, Uma and Linda. Next slide, please. As a background, the existing Transport Network Aware Mobility Draft defines a framework for mapping the 5G mobility service types to the corresponding underlying network paths. But the focus of that work was limited to the mobility domain. To extend that end-to-end transport network characteristics, the framework needs to be expanded beyond UPF. So in the current draft, it describes the framework for extending the mobility aware transport characteristics, how to maintain that from the UPF through the data network. Next slide, please. As an architecture, this solutions focuses in the following areas. The first piece is that how the mobility packet transitions happen in and out from the UPF to the CPE node, maintaining that transport path characteristics. The second part on the PE node, based on the transport characteristics, again use that different SRT mechanism to fetch the path segments and map that to a SRT segments with for the mobility hour transport packets. And the last part on the SDUN CE node, again based on that transport characteristics, the mapping could be done on a secured versus unsecured tunnel paths. Next slide, please. Yeah, so this diagram kind of represents the packet transitions from the UPF to the data network. The left side, the picture is from the mobility network, and this is captured exactly from that the TN-hour mobility draft. The right side is the data network. So this picture represents like how the management plane from the mobility sides can give the traffic classifications criteria to that IP network controller in the data network, and that rule could be propagated to the CPE node. So when the packets comes from the UPF, that would be that UDP header and the GTP header is already stripped. But when the packet arrives in the CPE node, using that same rule, the way that management plane provisions in the mobility side, same way it could put that UDP source port informations, which is basically the transport characteristics. And based on that, we could apply that outer header to maintain that SLA in that data network. Now, though, I just would like to mention one point here. In case the UPF and CPE are co-located in one device, in that case, probably we could use local policy, and that we don't need a control plane mechanism. The packet could be stripped, and the CPE can get that the UDP header informations, the source port informations, and then they could CPE could use that SRT rule. So that we will see in the following slides. Next slide, please. So the second part is that how we can map the transport characteristics to the SRT paths. Again, here the UPF is terminating that 5G mobility connectivity from the UE, and there are two scenarios that P could be sitting on a same device, or could be co-located, could be same device, or could be connected over an IP network. Now P node, based on the transport characteristics, again this draft proposes different mechanism to map to SRT segments. One is that the P is connected to a BGP SRT controller over the SR policy SAFI sessions, or P may be connected to a SRPC controller over the PCEP sessions, or we could have a RESTConf, a NetConf or gRPC sessions with a SRT controller, and we'll see like each scenario how we can map the transport characteristics. Yeah, next slide, please. Yeah, so this is the scenario, the first scenario, where that the P has that SR policy SAFI sessions with a BGP SRT controller. In this case, there is a new sub-TLV, 5G metadata sub-TLV is proposed that needs to be supported. There is no changes in the existing encoding, which is defined by the IDR segment routing T policy draft. So this sub-TLV captures the UDP source port start value and end value, and that's values are defined by the TN-hour mobility draft. So this is the format of that new sub-TLV, and I will see that next slide how it's we kind of apply. So next slide, please. Yeah, so in the BGP SRT controller, in this case, like a P1 has a SR policy SAFI sessions with a SRT controller, and that controller is provisioned somehow that UDP source port range, which is again defined. There are different source port range for MIOT, EMBB, and URLC traffic. And for that, we have a corresponding SRT policy configured. So when the SRT controller download the SR policies, so with that 5G metadata sub TLB could be downloaded. And when the packet comes, again, here we are kind of seeing the UPF and PE in the same node. When the packets comes here, based on that source port, UDP source port, if it falls within that range of that 5G metadata sub TLB bringing in, so then the SR policy would be applied, and based on that, like the packet will be followed. That's in the data network. It could be any type of SRT header. So the corresponding policy would be mapped, and the packet flows in the data network to maintain the SLA. So this is the scenario one. The next slide, please. Yeah. So this case kind of displays how the mobility integrations, KNR mobility integrations happen with the SRPC. So defines that class maps for the different traffic type, which is again the TNR mobility defines the MIOT, URLLC, and EMBB that has different source port ranges. So based on that, we could have a policy map which kind of set the colors for different traffic type. And based on the traffic type, there could be we could have a different metric type, and those types could be MIOT, URLLC, and EMBB. Once we have that, then next slide, please. Yeah, once we have that different mechanism, different metric type for that, the packets coming from the UV side to the PE. Based on that, once we classify, applied the metric type, then is PC request message will go with the metric type, and the segments could be downloaded, path segments. Once it is downloaded, then based on that SRT path segments would be applied. We would impose the SRT header. Again, it's any SR-MPLS, SR-B6, anything. It could work either one. So that way we would maintain that characteristics to that data network. And next slide, please. So next slide is the scenario 3. It doesn't have to be any. It can work with any. So basically, it's the captures is it can work with any mechanism, either SR policy SAFI sessions, or we could have a PSEP session, or we could have a RESTCON gRPC sessions with the SRT controller. In this picture, kind of it's assumed that it's a BGP SRT controller. So same way, the 5G metadata sub TLB with other policies could be downloaded over RESTCON for gRPCs. And it's pretty much the scenario 1. Once that UDP source port information is stripped out, that's based on that, like once we will see like which if it is which range it belongs, and based on that corresponding SR policy would be applied to carry over the packet over the data network. So that's how we kind of there are multiple ways this mechanism will work to map that the transport characteristics which is coming from that mobility sites will carry to the over the data network. Yeah. So next slide, please. So next, this slides it captures how we can integrate with a SD-WAN case. The earlier we saw kind of how we are integrating with the PE, ingress PE, and where it has a SRT connections with the controller. So here it's a in the more of a SD-WAN use case, and there is a BGP SD-WAN usage draft where it defines that SD-WAN use cases. So now in the hybrid use case, we will have secure tunnels and or unsecure paths like MPLS or VXLAN tunnels between the different edge nodes or cloud gateway. And in that case, again, UPF could be part of the SD-WAN edge node or could be connected over IP network. And this is the scenario, more of a scenario of enterprise 5G. Now, existing TN-hour mobility draft in the latest revision, it is expanded to which is pretty important for the mobile traffic. Now, based on that UDP source port characteristics coming from the mobile traffic, the SD-WAN edge node would be able to map either secure tunnel or unsecure tunnel. So next slide, please. Yeah, this figure captures between the two SD-WAN edge node connectivity. Here, one side is the CPE node, which is kind of co-located with the UPF. The other one is representing its cloud gateway, where we have a secure paths, secure tunnels established between the two endpoints, and we also have a MPLS path between the two endpoints. So when the traffic comes, again, based on that UDP source port informations, like if it is carrying that security characteristics, then the security would be given a higher priority, and then it would be applied. It would be applied to one of the underlay secure tunnel, IPsec-based secure tunnel, and the packet will go to the other side. And in case if it is coming without security characteristics, then based on the characteristics, MPLS or VXLAN tunnel could be used to take the packet to the other sides. Next slide, please. Yeah, as a next step, we need to get a ANA code allocations for 5G metadata sub-TLB. The SD-WAN use case also would be extended to integrate with a SRT-based mapping. So that's like not only just the security is kind of taken care, but with the security SLA also would be maintained when we have the SRT integrations. So comments are welcome. So I'll stop here. Yeah, Drew.
Yeah, hi, Kaushik. Even Stefan pointed this out, and we were discussing this on the chat, that FlowSpec would be a much better choice. It will provide you much more granularity for steering, and we already have a mechanism both in BGP and PCEP to do generic flow specification. So why did you not use that and instead define a new 5G metadata sub-TLB?
Show it to me, like you mean in the SR policy application case?
Both in BGP and PCEP, we have a flow specification where you can have much more granular control of defining which flows needs to flow in SR policy or even in any PCEP based tunnel. So we have much better techniques in my opinion. So maybe were aware of
No, I'm aware of that. I'm aware of that. But means not always the flow spec would be integrated in a network. Like this is means this kind of a this is a generic approach. Like already it has a P, already has a SAFI sessions or PCEP sessions. Like we anyway we need that kind of this metadata. The 5G this only captures the UDP source port. Start value and value. That's either you do it with the flow spec or kind of do it with the SAFI sessions. Not introducing sub-TLB for the SAFI sessions. For PCEP case, anyway, we need some metric type, and REST-conf, it's the same thing. So I don't see huge advantage, kind of. But we can discuss more. I'm open for if you have kind of other thoughts. We can talk more.
Sure, let's take this offline.
Yeah, sure.
Uma, do you want to unmute yourself? Yep.
Hi, can you hear me?
Yeah.
Okay. I just want to answer Drew. So this is, yes, flow spec can be used. Definitely, that will give much more granular flow specification at the UPF and PE combined scenario. But here the case is like the granularity is not required. Rather than he wants to maintain end-to-end SLAs. Like if your end-to-end SLA both in the mobility domain and the internet domain, if you want security or one of the SRT characteristics, he wants to maintain that. And you want to maintain the same characteristics that's used in the mobility domain, which is the UDP source-based port. So yeah, you can use both ways actually, to me.
Thanks, Umar.
I have a question as a working group participant. So you're limited by UDP 16-bit space. Why don't we looking up TID as well to make it TID plus UDP port source range? Uma, Kaushik, to either of you.
Sorry, can you repeat? What is that? Sorry, Jeff.
So
UDP source
now you're only looking up at the UDP source port range, so you're limited by 65,000 ports, right?
Correct. Yeah.
If you would look up TID, so GTP header next to
Okay.
UDP range, it would give you much better context.
Yeah. I think this is discussed in the DMM draft, Jeff. I think the problem is TID is a scalar. It doesn't represent the properties we are seeking, and the TID is overloaded with the 5G control plane characteristics. So we don't want to touch that, right? So that's the reason. We had a small calculation. One of the Texas guys, Future Wireless guys, they did the calculation of how many slices and how many characteristics can be done in a typical network. So that that calculation is there in the DMM draft. So we found out that for most practical deployments, the tunnel, the UDP source port ranges are good enough. Actually, the problem is we are limited by what you can put in the packet, right? So we don't want to enhance too many things in all the data planes. So that's why we are limited with that UDP source port. Yeah, it's kind of middle ground approach we took.
Okay, thank you.
Yeah.
Any other questions? So thanks, everyone. We are giving you 3 minutes back, and we hope to see you tomorrow. Have a good evening, morning day, everyone.
Yeah, thanks a lot.
But I'm feeling isolated again.
Tony, don't. We are with you.